Okay, so I've opened 3DEC, and I'm going to open the project that I've given you in the material that you can download associated with this course. So I open an existing project, navigate to where you put that training material. There's a directory called ground support, and inside of that is a directory called supported tunnel. And then here, when I'm doing the course live, we have the students create a new project and then follow along typing in the commands. For this video, instead we'll just open the solution that's already complete. So if you go into solution and open the supported tunnel project, we can just look at it and talk about it. Okay, so this is a model of a tunnel with a wedge in the roof, and we're going to try different types of support to prevent the wedge from falling out of the roof. So first we need to build the tunnel. As you've seen before, model new. As you've also seen before, block tolerance 0.001. So recall that there is a default tolerance that determines the smallest block that will be created when you make cuts. And sometimes you want to reduce that default to make sure that you have continuous cuts that go all the way through and you don't have asperities where you might decline to make a cut across a tiny corner or something like that. In this case, just to be safe, we reduce the tolerance from the default, which I think is probably about 0.01. You can find out the default by making a block and giving the command model list info, and it will tell you what the tolerance is. Okay, so I'm setting this tolerance. I'm creating a tunnel with this command. We may or may not have seen this before. This is a built-in command that just makes it easy to create a circular tunnel. It's probably not used that often in real life because you often don't have a perfectly circular tunnel, but for these types of simple examples, it's useful. If we just have a look at the help here, make this bigger, and I hit F1. So the command block create tunnel takes these keywords. So the number of blocks in the radial direction, the number of blocks in the tangential direction. Note that this is the number of blocks in a 45-degree segment. So the actual number of blocks around the tunnel is 8 times this. So we set it to be 2. So we actually have 16 blocks around the tunnel. The number of blocks in the axial direction, the distance of the boundary from the edge of the tunnel. And you can even set up a tunnel that is not perfectly horizontal. So you can give a dip and a dip direction. You give a length, you give an origin, you give the radius. And the radius ratio is the you can have the blocks getting bigger as you move away from the tunnel, which is often what you want to do. So in this case, we have radius ratio 1.2. We do not set a dip in a dip direction, so it assumes that it's extending into the positive y direction, and it's horizontal. So we can run this command, we can create the tunnel. We can just have a look at that part. So if we look at our block plot here, it's defaulting to group. I could change that to ID. You'll see that it creates a bunch of different blocks to define this tunnel. And at some point, we will join these together because these are not real joints. This is just a way to define the geometry. So first we create those blocks. We can give them the group name rock. We can give the blocks inside of the tunnel the group name tunnel by using range cylinder. And for range cylinder, you just give the coordinates of the one endpoint, the other endpoint, and the radius. So we set the tunnel radius to be 4. So what we're doing is saying every group that is inside of this cylinder with a radius of 4, we'll give it the name tunnel, and then we'll join everything. So we can run these 3 lines. Go back to our blocks. You can see it's now shows all one color because they're joined. But if I change the label back to group, you can see that everything out here is called rock and everything in the middle is called tunnel. Okay, we cut 3 joints. You've seen this before, block cut joint set. We give a dip direction, a dip, and an origin. What this will do is form a wedge in the roof of the tunnel. So if we run these lines, and go back and look at our blocks. We can change the label back to ID, and you can see how we've cut these joints, and this separates out different blocks. You can't really see it here, but you can believe me that this configuration of joints actually forms a wedge in the roof of the tunnel. We'll see it later. Actually, we can see it if we go to the joint plot. So here we're plotting blocks. You can also plot the joints. So I've given you this plot already. Oh, the blocks are showing here. So if I hide the blocks, you can just see the joints. So here are the joints that I cut. If I want to see the tunnel, I can turn on the block group, and under the color list, I can just uncheck the rock and leave only the tunnel. And so now I can see the tunnel. I can see the joints, and you can see there's up underneath here, there's going to be a wedge forming at the top of the tunnel. Okay, that's almost it for the geometry. The last thing we'll do is zone it. Here we're using the new zoning logic, and we've talked about this before. There's some old zoning logic in 3DEC that's been around for a long time, and in the last two versions, there's this new zoning logic that uses the same logic as Griddle to do the zoning. The reason that this is useful is that it ensures the new zoning logic. Okay, both the old zoning logic and the new zoning logic ensure that you have matching grid points across the joints, which is great. The old zoning logic does not ensure that you have matching faces across the joints. And so what this means is that sometimes you get interesting stress concentrations and things like that where the faces are mismatched across the joints. It's not a catastrophe because, again, the nodes are always matching, but the faces can be mismatching. So you can see some unusual stress concentrations and things like that. If you use this new zoning logic, it always ensures that the faces match, that the stresses look nicer. The only downside of the new zoning logic is that it sometimes fails when you have very, very bad geometries, if you have very skinny blocks or things like that. In this case, we don't. We can use the new zoning logic. And what we do is we set a certain zone size around the tunnel or in the tunnel, and then a different zone size outside of the tunnel so that we can have more detail in the region of the tunnel where we're interested. And then you just give this command block zone gen new, minimum edge length, maximum edge length. So let's run those commands. All right, there it goes. And now if we go back and look at the, oh, it's compressing. I have this set up to be automatically compressing the save files. I've shown that before. You can do it under tools options if you like. Okay, so if I go and look at my blocks, now I can see the zoning. You can see how we have smaller zones close to the tunnel and then bigger zones far away from the tunnel. Okay, we're done with the zoning. We go to initial. So here we restore this state. We set the properties. In this case, we'll assume that it's just elastic. Note that we're using megapascals here. So Young's modulus is 50 E3, so that works out to 50 gigapascals. And then be careful, you have to set the density to be kilograms per meter cubed divided by 1 E6 so that you have consistent units. The faults have a stiffness in megapascals per meter. This is the properties of the faults that already exist, and this material table gives the properties of the faults that do not yet exist but might form if we run this in large string. We specify gravity. Remember, we could actually do this more simply by just saying 10, and it assumes you mean the gravity is acting downwards in the z direction. We specify the in situ stress state. You remember this command block in situ topo. So what it does is it automatically works out the vertical stress based on the weight of material over each zone. And then you give a ratio of horizontal to vertical stress, in this case 0.5. This works great if the top of your model is at the surface of the Earth. In this case, we want to assume that the tunnel is actually quite deep. So what we do is instead of modeling 176 meters of material above the tunnel, which would just slow everything down. We account for this 176 meters of material by adding a force, installing an initial stress into the system as if there was an extra 176 meters above our head. So what you can do is with this block in situ topo command, give an overburden. And the overburden is just the weight of material above your head or above the top of the model. And here I'm working it out with some inline fish. So 176 meters times gravity, which is 10, times 0.0027, which is the density. Note that it's negative because compressive stresses are negative in 3DEC. So that will install the initial stresses. The boundary conditions, so we've seen this before, we're fixing the sides. In the x direction on the left and right side, we're fixing the y velocity on the front and the back. We're fixing the z velocity on the bottom. On the top, we're applying a stress that matches this overburden stress. So this is exactly the same calculation we have up here. This stress that we're applying to the top should balance the overburden stress that we installed with the in situ command, and we're applying that to the top. We're taking a couple of histories here, the ratio, the force ratio, and a vertical displacement of a point in the roof of the tunnel, turning on large strain and solving and saving. So we can run this whole file. It should run quite quickly because the installed stresses and the boundary conditions should be more or less balanced. Notice here that I'm setting a ratio smaller than the default. By default, the unbalanced force ratio that it solves to is 1e minus 5. In this case, I'm using 1e minus 7 just to get a more accurate solution. Okay, it's saving that. We can go have a look at our blocks. So here's the label. We can change this to contour by displacement. Right, we see a little bit of displacement here around the joints, but it's very, very small, 1.27 e minus 5. So it's not anything to worry about. We can check the stresses to make sure that we installed the stresses correctly. So if we change the contour to stress, goes to XX by default, we can change it to ZZ. See the vertical stress. And again, compression is negative, so this is slightly disconcerting with having red at the top and blue at the bottom. You can flip it by pressing this checkbox here in the attributes where it says comp positive. So that changes to be compression positive. And now I see something that looks a little more sensible with low stresses at the top and high stresses at the bottom, as we would expect due to the loading. Okay, so that's the initial state. We haven't done anything yet with the tunnel. So the first thing we will do is I'll just set this running while I talk about it, because it does take a couple of minutes. We restore the initial state and we delete part of the tunnel, so 4 meters worth of the tunnel. We're deleting range group tunnel position Y minus 10 to minus 6. So a 4 meter chunk of this tunnel, and then we're solving and saving. Then we're deleting the next 4 meter chunk from minus 6 to minus 2, solving and saving. Then we delete the next 4 meter chunk, minus 2 to 2. At this point, we have excavated past where the wedge is, and so this does not solve. You can try it. If you say model solve, it never solves because that wedge is falling out of the roof. You have a disaster, and it doesn't reach equilibrium. So what we do here is we add a safety valve, and we say it's going to try to solve to 1e minus 7 or 2,000 cycles. If it doesn't get to 1e minus 7 in 2,000 cycles, it will stop and it will save it. So we can watch the model as it's solving here. So if I look at my block plot, let's change this back to displacement. So it's kind of interesting. You see how you're getting a little bit of displacement along these joints, but it's still not very big. We're talking millimeters here. That's okay. Now it's doing the third part of the tunnel, the third 4 meter chunk. Now, if we zoom in here, you can see the wedge in the roof, and you're seeing some high displacements here. So now you can see this wedge is really moving. and you can look at the mechanical ratio here, it does not solve. At least it does not solve to the criterion of 1e minus 7. So it's saving it. So you can see this wedge by color. If you want to emphasize the movement, you can exaggerate the displacement. So if I click on block displacement magnitude, under the attributes, there's a checkbox for deform. So I can exaggerate the deformation. I can choose whatever number I want here. So I put in 20. And so this exaggerates the displacement by 20 times, and you can really see the wedge moving here. Alternatively, I could just keep running more cycles, and you would see this wedge moving. It just falls out and eventually hits the bottom of the tunnel. Okay, that's what happens if it's unsupported.